Alright, we got number 25 on the AMC 12 here. I hope you got your popcorn, because we're probably going to be here for a while. After all, we're starting with the parabola. We're definitely going to be here for a while. Start with a sketch of that parabola. Focus is at the origin. Goes through 4, 3, negative 4, negative 3. Well, these points, of course, they're collinear. And the origin's the midpoint of the segment connecting these two. Now what? Alright, these 2 points are on our parabola, so this is a chord of the parabola. These 2 points are each 5 away from the focus, and that tells us something a little bit more, because a parabola is the set of points equidistant from a focus, and some line we call the directrix. So each of these points is 5 away from the focus. That tells us each of these points is 5 away from the directrix. So we're looking for a line that's 5 away from each of these 2 points. Well, there's one line that goes right through the middle, the perpendicular bisector of this segment. But that can't be the directrix. Directrix can't go between 2 points on the parabola. There are 2 other lines. There's one down here. It's parallel to this. There's one up here. It's parallel to this. It's a very special chord right here. So whichever one of these we choose, this chord is parallel to the directrix. The chord has a funny name. It's called the latus rectum. So the chord goes through a focus. The chord that is bisected by the focus, it's the latus rectum. It's parallel to the directrix. Which directrix do we choose? Do we want this one or do we want that one? I have no idea. Let's read on. We want to find how many points on the parabola with integer coordinates, we're looking for lattice points, satisfy this wacky condition. Now, I don't know what to make of that condition, but I know what to make of lattice points, points with integer coordinates. So let's think about the lattice points on this parabola and how they're related to the lattice points on this parabola. Well, you get one parabola by rotating the other one by 180 degrees. So that's how these 2 parabolas are related. You just rotate one 180 degrees, you get the other one. Now when you rotate a point 180 degrees, rotate 4, 3, 180 degrees, you get negative 4, negative 3. Just negating coordinates, just put it around. So if a lattice point satisfies this condition, you rotate 180 degrees, and that's going to, point you're going to get is going to satisfy this condition as well. Moreover, if you take a lattice point and rotate 180 degrees, you're going to get a lattice point. So all the lattice points on this parabola, you rotate them 180 degrees, you get lattice points on that parabola, and anytime one of these lattice points satisfies this condition, so does one you get when you rotate it 180 degrees, so it doesn't matter which of these parabolas we think about. Now I'm an optimist. I'm going to choose the one that opens up. Well, up is a relative term. We're going to call it up-ish, because it doesn't open directly up. It doesn't open directly up. It's crooked. And that's terrifying. I have no love at all for this because our directrix is not horizontal, it's not vertical. So we get this kind of crooked parabola thing. And I break out some distance formula and stuff like that, but I don't like thinking about parabolas like this. I like parabolas that open up, straight up. I'm even good with ones that open down, open left or right. The directrix is horizontal or vertical. Those I'm good with. But this crooked stuff, this won't do. So here's what I want to do. I want to spin this puppy. I want to spin it so it looks the way I want it to look. But I can't just will it to spin. I have to spin it myself. So we're going to spin this. Now, I don't know how to spin a parabola. So I'm going to start by spinning one point. We're going to spin xy. That's what we're going to do. We're going to start with xy. And when we spin xy, okay, I don't know how to spin xy either. Spinning rectangular coordinates, that's hard. But you know what's easy? Spinning polar coordinates. Spinning polar coordinates is easy. If I start with r theta, spin that about the origin, I'm going to get r theta plus phi. We're spinning it by phi, and that's nice. But our problem's in rectangular coordinates, not polar coordinates, so alright, but I know how to relate rectangular coordinates to polar coordinates, so maybe we're going to learn something about rotating in rectangular coordinates. So rectangular coordinates related to polar coordinates. X is r cosine theta, y is r sine theta. So now we're going to spin, we're going to rotate, we're going to take xy and I'm going to send it to something, I'm going to call it uv. We're going to try to figure out what uv is in terms of all this r, thetas, phis, and all that sort of stuff. We've got uv, we're spinning this to get to that, it's the same thing as spinning this to get to that. That means uv in polar coordinates looks like that. So that's r cosine theta plus phi r sine theta plus phi. Now what? It's a very special problem-solving technique. If there's only one thing you can do, do that. The only thing we can do is break out the angle sum formulas here. Cosine of an angle sum, sine of an angle sum. And the reason I'm not too scared about that is look what happens when we just start doing it. Very first step is r cosine theta, cosine phi, and we see that r cosine theta and we say, hi friend, we've seen you before, that's x. So we might be doing something good here. So we keep going with this identity, minus r sine theta, sine phi. And then we do the same thing over here. We get r sine theta, cos phi, plus r cosine theta, sine phi. And r cosine theta, that's x. R sine theta, that's y. R sine theta, y. R cosine theta is x. So we can clean this up a little bit. Make those substitutions. We get x cos phi minus y sine phi. And over here we have y cos phi plus x sine phi. Okay, that's nicer than this, but it's not what I'd call nice. What are we trying to do here? Oh yeah, we were trying to spin this parabola, make it look like that, make it look nice. Vertical axis of symmetry. Now if we do that, we spin that parabola, we're going to take this point 4, 3 down to the x-axis. And keep the origin right there, keep the focus right there. We're going to spin that 4, 3, and it's going to go down here. It's going to go to 5, 0, because it's still going to be 5 away from the focus. So we want 4, 3. And xy of 4, 3, we want the 4, 3. We want that to go to 5, 0. So now we just have to choose the right phi. We have to choose the right angle so that when we put in 4 for x and 3 for y, the out pops 5, 0. So what angle is going to do that for us? When I'm seeing all these 3, 4s, and 5s, we figure our angle is going to have some 3/5, some 4/5 in here among these sines and cosines. But now one of them is going to have to be positive. One of them is going to have to be negative because we want this to come out to be 0. So they're going to have opposite signs, SIG and S. But which one's which? Which one's going to get the positive? Which one's going to get the negative? Well, we look back over here. We want this to come out to be positive 5. So we're going to choose the sine SINE to have the negative, sine SIGN. Sine SINE will be negative, cosine is positive. One's going to be 4/5, one's going to be 3/5. We want these to cancel out. We're going to let this one be 4/5. We're going to let this one be negative 3/5. All right, and that's a fine sine and cosine because just add the squares of those, you get 1. So this is perfectly valid. There is a phi out there that satisfies this. That goes to 0. What happens over here? We stick in 4/5. We stick in negative 3/5. And sure enough, we get 16 over 5 plus 9 over 5. That's 25 over 5. That is 5. We've gone from 4, 3 to 5, 0. We have our rotation. We can get from this parabola to this parabola. And that rotation we can describe with this transformation right here. We have 4/5 for a cosine phi, negative 3/5 for a sine phi. So we get uv from 4x plus 3y over 5. And then over here we have 4y minus 3x over 5. All right. We're getting somewhere now. You know how I know we're getting somewhere? Look at that. 4x plus 3y. There's that wacky condition. This is a terrible condition. I don't know how to think about this. But this 4x plus 3y magnitude has to be less than or equal to 1,000. I look at this. And now this condition, which is horrible up here, is simple here. 4x plus 3y divided by 5. This thing has to be, the magnitude of this has to be no greater than 1,000. This means the magnitude of u has to be no greater than 200. It's way easier to compare u to 200 than it is to compare this mess to 1,000. So this is my first clue that I'm doing something right. Took us a long time to get there, but I'm at least confident that we're eventually going to get there. So now we've rotated our parabola. Rotated our parabola looks like this in the UV plane. Still have the focus at the origin. Now the 2 points have been rotated onto the x-axis. 5, 0, and negative 5, 0. And we know where the directrix is too, because focus is 5 away from each of these points, so each of these points are 5 away from our directrix. It sits down here. V is negative 5. And that tells us our vertex is right there at 0, negative 5 halves. We see our parabola. It sits right in here. And we can write an equation for this parabola. That was the whole point of rotating it in the first place. This parabola, opens straight up. It's going to look something like this. V equals some constant times u squared. And it's going to be minus 5 halves, because we know that when we stick in 0 for u, we've got to get negative 5 halves for v. Now we can figure out what this constant is too by using this 5, 0 that sits out here. You stick that in there, you're going to have 25 times k minus 5 halves. That has to be 0. That tells me that k is 1/10. So v is 1/10 u squared minus 5 halves. I stick 5 in there. Sure enough, I get 0. Clean this up a little bit. I'm going to multiply through by 10. 10v equals u squared minus 25. Of course, I can write that as u squared equals 10v plus 25. All right, now we're ready. We've got points to satisfy this equation. U has to range from negative 200 to 200, and x and y have to be integers. No x and no y. Still not done. Okay, here we go. We know how u and v are related to x and y. We have u and v related by that nifty little thing we got out of our rotation. All right, they're related like this. And we know something about u and v now. We know that u squared has to equal 10v plus 25. However, we don't know that u and v are integers. We only know that x and y have to be integers, so we have to figure out when integers x and y will give us u and v that satisfy this equation. We have to use that x and y being integers thing somehow, so we're going to have to take this, jam it in there, and that's no fun. I see the fractions coming from a mile away. I'm going to get out in front of that. I'm going to multiply by 25. All right, multiply by 25 first. So then when I stick these in, when I put that in here, it's going to square this up. I'm going to get a 25 in the denominator. It's going to cancel with that. So I have 4x plus 3y. At the very least, that saves me a little board space. I'm going to put this in here. I'm going to cancel out a factor of 5 and a 50 times 4y minus 3x. I still have the 625. And what does that give me? Well, at least now x and y are integers. X and y are integers. That tells me that this side of the equation is a multiple of 5. It tells me that this has to be a multiple of 5. It tells me that this has to be a multiple of 5. 4x plus 3y has to be a multiple of 5. That tells me that u is an integer. That makes me happy. That makes me really, I'm going to even write that down because it makes me so happy. I'm going to really know. Math geek speak, u, this little funky in symbol, and that little z that means the integers. U is an integer. This is very good. But you know what would make me really happy? Is if v were an integer too. Because if v were also an integer, then I could stop thinking about this awful equation and just think about this pretty equation. This is much nicer than that. So let's see about that. I know that u is an integer. I want to see if v is also an integer. All right, we remember how u and v are related to x and y. Once again, can't forget that. We have this so far. And now we've discovered, that is an awful 3, we've discovered that u is an integer. That means that 5 divides 4x plus 3y. But what we really want is we want 5 to divide 4y minus 3x. We want to go from here to there, because then v will be an integer too, and that'll be awesome. Well, how do I do that? Well, I can get from 3y, check this out, I can get from 3y to 4y like this. If 5 divides this sum, then 5 also divides 3 times this sum, which is 12x plus 9y. Because if I divided this evenly, multiplying by 3, I'm still going to divide it. Now, if 5 divides this, well, y is an integer, so if I subtract 5y from this, I'm going to go from one multiple of 5 to another multiple of 5. So just like multiplying by 3 gives me another multiple of 5, subtracting a multiple of 5 gives me yet another multiple of 5. So I just subtract 5y, and 5 divides this, and now I've got my 4y. And now we can see where we're going to get our minus 3x. We're going to subtract another multiple of 5. We're going to subtract 15x. X is an integer, so that's a multiple of 5. I subtract my 15x, and sure enough, 5 divides negative 3x plus 4y. That tells me v is an integer. And now I'm really happy. V is an integer too. I'm going to write that again because I like writing that little funky Z symbol that stands for the integers. U is an integer, V is an integer. I don't have to think about this equation anymore. I can go back to this one because now I'm looking for integer solutions to that equation. That's a lot nicer because I look up here and right away I see U is a multiple of 5 because this side is a multiple of 5. So U has to be a multiple of 5. I'm going to call U. It's going to equal to 5 times A for some integer A. I'm going to stick that in here. We're going to get 25A squared equals 10V plus 25. Well, I see where this is going. V is a multiple of 5 as well, because here we got a multiple of 25. Here we've got a multiple of 25. That means this has to be a multiple of 25 as well, so I need another factor of 5 in there. I'm going to drop in a little V equals 5B. Action, drop that in here. Now I've got 25A squared equals 50B plus 25. Divide everything out by 25, and we've got something much cleaner to look at. A squared is 2B plus 1. And A and B are integers, so A is odd. A is odd, so now I can write U as 5 times 2C plus 1 for some integer C. That forces A to be odd. I'll put that in here, go ahead and square it out, and I have 4C squared plus 4C plus 1 equals 2B plus 1. So those 1's are going to go away. I'm going to be left with a multiple of 4 over here. It means I need a multiple of 4 over there. It tells me B is even. So V is 10 times something, times some integer. I stick 2D in for B, and I'm going to have 4C squared plus 4C equals 4D. I can knock out the 4's, and now I know that C squared plus C equals D. Whew. What does that tell us? So here's what we've learned so far. We've learned that if we have a lattice point on this parabola, all right, and then we spin that parabola, we've proved that it will land on a lattice point here, because we showed that if x and y are integers, then u and v have to be integers as well. And then, well, we went and looked for the lattice points that satisfy this equation, and we found, worked through all this algebra, and we found that if u and v are of this form, if I take c to be any integer and stick it in here, so u comes out to be any odd multiple of 5, 5, 15, 25, then I'm going to get a lattice point. So I take that c, put it in here, I get a value of d, and I use that to get v. And that gives me my coordinates u and v that are lattice points on the parabola. So that means my lattice points on this nice parabola happen everywhere where u is an odd multiple of 5. And we remember from before what our condition was. U is this right here, is 4x plus 3y over 5. We need the magnitude of 4x plus 3y to be no greater than 1,000, so u has to be no greater. The magnitude of u has to be no greater than 200. So coming back here, these odd multiples of 5, they have to be between negative 200 and positive 200. Well, it's easy to count those. You know, it's a span of 400. You get 1 every 10. There's 40 of those. So now, of course, you're going to go back. You're going to look at the choices. You're going to say, hey, there are 40 of these u's. There's the answer. It's 40. Because we found that there are 40 lattice points on the nice parabola that goes like this. And we saw that every single lattice point that was on this rotates onto a lattice point of this. Now, you'd be forgiven for just circling 40 and moving on. I mean, clearly the answer can't be 42, 44, or 46. But there's a little wrinkle here that we have to be careful about. All we've shown is that every single lattice point that was on this, when we rotate, becomes a lattice point on the nice parabola. We didn't show that every lattice point on the nice parabola comes from a lattice point on this. So it's possible that in these nice 40 lattice points that we have here, 38 of them come from this rotation. You know, they map nicely from a lattice point that's on this parabola, but there might be 2 renegades, 2 really mean lattice points that pop up out of the blue. Now that's probably not going to happen. We should check it out. We're going to go ahead and check it out because we have the time. We don't have a time test here. We're going to go ahead and find out exactly why every single one of these lattice points for u and v come from some lattice point x, y. Now, how are we going to do that? Well, we could run this backwards. Solve this for x and y in terms of u and v. It's just a system of equations, just linear equations. You can do the algebra, and we can even jam these things in here. That sounds like a mess. But instead, I'm going to do something a little clever here, because being clever is a little bit more fun. How do we relate uv and xy? We did this rotation. We rotated by phi to get from xy to uv. So how do we get from uv back to xy? We just rotate back. We rotated by phi. We rotate back by negative phi. And what happens in all this mess when you take phi and replace it with negative phi? What happens with the cosine? If we replace phi with negative phi, nothing happens to the cosine. Cosine phi is the same as cosine negative phi. The sine of negative phi is the opposite of the sine of phi. All right, so all we have to do here to go backwards is flip the signs S-I-G-N-S on the signs S-I-N-E-S. So that's how we're going to go from this to something that looks just like it with the x's and y's in terms of u and v. So here's where we were to begin with. We had this. All right, and that's how we take any x, y, and we turn it into a u and a v. And then we were back here and we saw that, hey, wait a second, all we have to do is flip the signs S-I-G-N-S on the signs S-I-N-E-S. So I'm going to take each of these minus 3/5 and turn them into positive 3/5 to go the other way. So I need to just flip the signs S-I-G-N-S on the 3's to run this thing backwards. To get xy out of uv, we flip the signs S-I-G-N-S, and that is how we'll run it back as a v. We'll go from uv back to xy. And now we see our expressions for u and v. We see that they're always, all these lattice points uv that satisfy our nice parabola, the u and the v, always multiples of 5. So these are always going to come out to be integers. So we come back here and we say, hey, those 40 points that we found on the nice parabola, they go with 40 points on the awful parabola to satisfy this condition. The answer is B, and we are finally done.